Guys, just think of an identity as a shortcut. In math, it's basically like a formula that you can use to speed up a normal process. Look, and I've got examples of the 4 up here. Guys, we don't have to read through this, all right? This definition says a mathematical statement that equates 2 polynomial expressions is an identity. For short version, guys, an identity is kind of like a shortcut, all right? But we got 4 of them that we're going to use in this section that's in our standards, all right? First example.
Can I get it?
Hang on.
I'm
going to take example 1, and then I'm going to let y'all do try 1. All right, guys. In math, we hadn't done a bunch of this. Coach Ron, in his graduate course, I do it every single day. I submit homework. In math, there's something called proofs or proving something. For us in algebra, you're trying to show that the left-hand side of an equation is equal to the right-hand side. All right, and in doing so, I know this is backwards to how we normally like to think. But if you're trying to prove something algebraically, all we're trying to do is show that this left side is actually equal to this right-hand side. When you do that, you want to start on the more complicated side. Here's why. We're going to be able to do a little bit of math over here, and hopefully things will clean up to equal just a cubed plus b cubed. All right, so here's what we're going to do. We're going to start on the right-hand side, and in 4.1, we looked at how to multiply a binomial times a trinomial. What would I have to do if I wanted to multiply this times this? You could definitely do the little box method. I think a lot of us in here are using the box. But basically, I just need to distribute A to all 3 parts. What's A times A squared? If I multiply A to the first power times A to the second power, A cubed. What about A times negative AB? Positive A times negative AB. Negative, and you got A to the first. I didn't mean to write over to B there. You got A to the first times A to the first. So that's going to be A squared B. We're only doing this on one example, so don't get too weirded out by it. We're just showing these 2 new relationships we're going to use today, these 2 new identities. All we're doing here in the beginning is just showing that they actually are true. That if I multiply this thing out, I will get this expression over here. So we did A to the first times A squared, A to the third. A to the first times negative AB is A squared B. What about A to the first times B squared? Would you say B cubed? You can only do that if it was B times B squared. Guys, when you multiply different variables, you literally just write them together. There's no actual multiplication you can do. So all we did right there is distribute the A. I don't need anybody checking out on this example. All we're doing is just proving that this works, and then we'll show how we're going to use it in a second. And then right here, we got B to the first that we're going to be distributing. What's B times A squared?
BA squared.
All right, BA squared. And I'm going to write it the same way we wrote the one before with the A squared first. Instead, Kelsey said BA squared. That is the exact same thing as A squared B. Multiplication is commutative. You can swap it around. And then I do B times negative AB. I got B to the first times negative AB to the first. Negative AB squared. And then the last piece, you got B to the first. Landra, B to the first times B squared.
B cubed.
B cubed. So, long story short, when we start combining like terms, Landra, what do you think what do you think happens when I have negative AB squared plus AB squared? I said that wrong. Let me do that again. What do you think you get when you do negative A squared B plus A squared B?
It cancels out.
Yes, ma'am. Guys, they cancel out. Landra, what about AB squared plus negative AB squared? Cancels out. What are you left with? which is what we were trying to show. We were trying to show that the left side was equal to the right-hand side, and we did that. I know that's a little weird because there were no numbers. It was all variables, but we just proved that this identity is true. All right, y'all do try it one real quick. Try it on your own. Hey, buddy. When you multiply, yeah. All right. All right, guys, for time. Look, I won't go over every single try it today, but this one I wanted to real quick. We don't do a lot of proving like that probably as much as we should in here. So look, when we prove this, we start on the right side. We're trying to show that it just equals a cubed minus b cubed. Distribute a. Now come back, and I do treat that like negative b. Negative b times a squared. I'm going to put the a first. If you do negative b times a squared, that is negative b a squared, which you're more than welcome to rearrange. I just wrote it the same way I had it the first time. And then I've got negative b times ab. That's negative ab squared. And then negative b times b squared, negative b to the third. Guys, anytime you're doing basic algebraic proofs, something should start happening to start making one side look like the other. Here we got opposites. Here we got opposites. And that's going to leave me with just a cubed minus b cubed, which is what we're trying to show that it was equal to. All right. Anybody still need this before we head on? Guys, the name of those two identities we just proved, you have not used these before. You have seen these, definitely. These two are brand new. I want to start by just us proving that they actually are true. All right. We won't use those to the very last example. Example 2. All right. Guys, example 2, it says we're going to use polynomial identities to multiply expressions. It says name and use a polynomial identity to multiply these. Devin, look at this. It's 2x squared plus y to the third squared. Of these 4 identities over here, of these 4, which one of those do you think it looks the most like? Let's go through it. Okay. Why was it not difference of squares? What's difference mean? Yeah, but in math it means subtraction. There ain't no subtraction. Guys, in difference of squares, it's got to look something like this. All right. Anyways, and you said the square of sums. I'm gonna write that up here. I'm not gonna write square of sums, but I'm gonna write that. That does match the way this problem's written. Look at this. You got a binomial squared. Binomial squared. Anytime you got that, you are more than welcome to use this identity. I'm gonna write it right here, underneath it. It told us to name which identity. This is an example of the square of sums. This is probably, some of y'all are going to be like, oh, coach, that's super easy. Some of y'all are like, not real sold on this. But let's do it using this pattern. Hold on, let me write the whole thing out, sorry. All I did is I'm using this identity right here.
Okay, but why would you use, like, what's in front of the equal sign and not, like, how would you do it last time?
Why not flip-flop it?
No, like, I don't know, I guess.
Landry, you're going to be one that I'm going to say this over here in just a minute. Okay? When in doubt, multiply it out. Let me do it. Let me do it using the identity first.
Thanks.
What?
Thanks.
That wasn't an insult. I'm going to recommend that to every block today.
Yeah, but you just had to call me out like that.
I was just saying you're good at multiplying them. We just talked through some of them. Look, that was not an insult. Guys, look, these identities are just shortcuts. You can always do it the long way. I just wanted to show you how to use the shortcuts. The way this works, Devin told us that this matches the square of a sum. If we can just identify what A is and what B is, we can plug in and save a little math. So right here, what do you think A is, anybody?
2x.
That's A. So A equals 2x squared. What do you think b is?
Y cubed.
All right. If you want to use this identity, a is 2x squared, b is y cubed, all Coach Braun's going to do is I'm going to go replace a with 2x squared in the formula. That used to say a squared, it now says 2x squared squared. In the middle here it said 2 times a, I replaced it with 2x squared, and then b is y cubed. Everywhere I got parentheses, that's me substituting in what a is and me substituting what b is. All right, and then the last part said plus b squared, so I got y cubed squared.
Why would you square that?
Because that's what it says in the identity here. It says b squared.
Oh, I didn't see that.
That's all right. And then from there, guys, you just do some simplifying. When I square 2, what's 2 squared? 4. When you have an outside exponent and an inside exponent, you multiply them. So what's x squared squared? X to the 4th. If you don't want to do this, I got my little note over here. Right here in the middle, I got 2 times 2x squared times y to the 3rd. Devin, what do you think I'm going to get when I multiply 2 times 2x squared times y to the 3rd?
4x squared and 2y cubed.
You just multiply 2 times 2, and that's an understood 1, which you said 4. Then it's just x squared y cubed. Devin, what do you think y to the 3rd squared is? When you have that outside exponent, you just multiply it times the inside. So what is it for sure? Okay. If that's a little weird to you, because it always is to some students. It always is. All it's intended to be is a shortcut. And it probably didn't feel like a shortcut the first time you see it, but I do want you to know, when in doubt, just multiply it out. Like if you don't want to use that identity, what you could have done is drop your yardstick. Thanks, man. Guys, check this out. All it said, it was 2x squared plus y to the 3rd squared. So you just do it times itself. Landra, you just told me about one like this over there on a previous section. Like if you wanted to, you could just rewrite this times itself, and then just distribute it. And
Yeah,
you get.
that's what I was trying to ask. Like,
You are more than welcome to do this. 2x squared times y to the 3rd is 2x squared y to the 3rd. Then distribute. Guys, all this is a shortcut of distributed property. And if you think distributed property is easy, I'm not going to force you to use those. I just want to show them to you because that's what you're supposed to see them in here. Y to the 3rd times 2x squared is 2x squared y to the 3rd. And then y to the 3rd times y to the 3rd is y to the 6th. Add those. You get to the same exact place. For try it 2, what would A be?
3x squared.
What would B be?
5y cubed.
So if you use, I'm not going to rewrite the identity. You would do A squared. So 3x squared squared plus 2 times 3x squared times 5y to the 3rd. All I'm doing is plugging in. That says A squared. I put 3x squared squared. That's at A squared. I did 3x squared squared. And then it was 2 times A times B. And then the last part is B squared. So that's 5y to the 3rd squared. Catherine, what's 3x squared squared? Let me ask it better. What's 3 squared? Say again. 9. What about when you got x squared squared?
4.
X to the 4th. When I multiply this mess in the middle, 2 times 3 times 5.
2 times 3 times 5.
I'm just multiplying the numbers. 2 times 3 times 5.
30.
2 times 3 is 6. 6 times 5 is 30.
I think.
Yeah. And then x. There's nothing to do with your variables there. And then this last part, Catherine, what about 5 squared?
25.
And then what about y cubed squared?
Y 6.
All right. Guys, identities are supposed to be shortcuts. Some people look at this and that makes a pile of sense. If you're iffy about it, guys, you can just do the distributive property. They're intended to be shortcuts, but the first time you see them, it's a little iffy. Well, the only reason I like this lesson is it reminds us, we have not had this pop up in my class a lot. When you have an outer exponent, you apply it to the number in front, and you apply it to any other exponents inside there. Let's roll on. Guys, I'm gonna leave try at 3. I'm not gonna go over it. Look at example 3. What's the only difference in example 3 and the one we just did?
There's no exponent thing or
Okay, there's no exponent with a y. What's the big? There's a bigger difference.
there's no number in front of it.
I agree, Landry. You have said there's a 1 and then it didn't have an exponent. I agree.
And it's subtraction.
That's the key, guys. Sometimes some textbooks teach this as a totally separate identity. I like to teach it as the same exact one, but this time we're going to use the same identity we just used, where we do a squared plus 2ab plus b squared. Obviously, a is 6x squared, but where I don't have to teach you a separate identity, we just need to make sure we let b be negative y. And then you just do the same process. I'm going to go replace this with 6x squared. All I'm doing is plugging in my a's and b's. If you still don't like it, just multiply it out. Kendall. Let's simplify this thing. Kendall, what's 6 squared?
3.
Try again. Either with a calculator or just do 6 times 6 yourself.
6 times 6.
Yes.
36.
All right. So 6 squared is 36. Kendall, what about x squared squared? Just multiply your exponents there. You ain't gonna be able to put that in K. 4. What are they working on? I'm gonna take the middle here. Guys, that's just 2 times 6 times negative 1. What's 2 times 6 times negative 1?
I'm sorry.
All right, I have a hard time focusing when that stuff's going on.
Because,
2 times 6 is 12.
okay,
Times that negative 1,
negative 12.
that's just going to be negative 12 x squared y. It's the same thing as the previous example, except the sign in the middle is going to be negative. Some textbooks give a totally separate identity for that. If you did want to just use this identity, it would be minus 2ab plus b squared. But I say treat it the exact same. And then this last part, I got negative y squared. What do you think negative y squared is?
Negative y to the 4.
What's the exponent 1. So 2 times 1 is 2.
Wait. I'm sorry. I messed up.
That's okay. Guys, when you square anything, it's going to be positive. Negative y squared is positive y squared.
How?
Because if you do negative y times negative y, that's like negative 1 times negative 1, which is positive 1. Y to the first times y to the first is y squared. You get 1y squared. Guys, I'm going to hold off on breaking. I know some of y'all are struggling, needing a break, but let's power through. And I'll stop. I'll stop early on the back end. Look, anybody got a question about example 3? Same as example 2, except the negative sign. And guys, at the end of the day, if you just aren't getting how to use the identity, all you would have had to do on the one we just did is take 6x squared minus y. And some of y'all have been putting them in the box, doing the box method. You can box it up. I'm not going to work it out, but you would have done this right here. You'd have just done your little box. You'd have done 6x squared negative y, 6x squared negative y. I could tell last week, the day we had a lot of people missing, y'all were putting them up here and y'all were rocking it. You can do all of these that way. If you are good with the box method or distributed property, you're going to get the same exact answer we just got right here. All right. Example 4. Which one, if we're going to use an identity, which one does that look like?
Difference of squares.
Why did you say that, Catherine?
Because it's a positive and a negative.
All right. You got the exact same numbers and variables, except one's plus and one's minus. I definitely, guys, while the other one is 100% optional, I think this one is extremely useful to know.
I didn't get that. Could you try again?
Yes, ma'am. Guys, the difference of squares works out pretty sweet. Yes, you could go off to the side, do the box method or distributed property, and get the same exact answer we're about to get. But really, you can take a gigantic shortcut here. What would A be here? A is, look at our parentheses. A is what comes first in the parentheses. So A would be 2x squared. Oh, y'all are saying when I plug it in. In just a second, I'm going to plug it in. You will get 4x to the 4th. Guys, I do see a typo in these notes that I'm going to have to fix before next block, or third block. We actually, the way it's written, you would not be able to use the difference of squares because Coach Brian left off this little exponent. That should have a 2 there. That's my fault. I will throw this whole set away and print some new ones. But guys, A is what comes first in the parentheses. Is 2x squared. What do you think B is? Even if you didn't like the square of sums, or it wasn't like a shortcut to you and you'd rather just distribute, it is nice to know this one because you can just square A. So 2x squared minus B squared, which is 5y. This is a pretty good little shortcut, I think. Let me see. Sadie's not here. Jackson, what do you get when you square 2? What about when you multiply those exponents? It'll be x to the 4th. What about right here? 5 squared is 25. And then y to the 2nd. Guys, the difference in squares works out pretty sweet. Like this one. This is another difference of squares. What would A be on try it for? X cubed. What about B? So we're doing A plus B. We know that when we multiply A plus B times A minus B, You're just going to get whatever a squared is. So write that down. X to the third squared minus 7y squared. Jacob, right here when I got x to the third squared, what are you going to get when you multiply those exponents? Second, x to the sixth. Guys, a common mistake is to not apply that outside exponent to the actual number. Jacob, what's 7 squared? 49. And then how about the 2 times 2 there? Y to the 4th. For my distributed property or box method people, you could absolutely 110% go off to the side. I really wasn't trying to rhyme when I said that, but when in doubt, just multiply it out. If you would rather do that, you're going to get these same answers. Questions so far? They're intended to be shortcuts, but again, if you would rather multiply them a different way, you're welcome to. Or I shouldn't say a different way, using distributed property. All right, last example. Guys, this is the big way, and those of y'all who have participated, you can get a piece here at the end. Guys, this is the big way that you can't go off to the side and really do it this way. You can also use these identities to factor. If you remember, we factored in that unit 3. We did this easily signed trick, all that stuff. But using identities to help us factor is just the reverse of distributed property. We want it, these are factors. When it's written with parentheses as multiplication, those are factors. If a problem or if an expression fits one of these identities, you can factor them this way. Come on, y'all. Refocus. 3 minutes. All right. I'm going to take example 5a. I realize you have exponents of 4 and 6. But look at your numbers in front, 9 and 25. I'll give you a hint. When you have even exponents and you have perfect squares in front, you can still apply the difference of squares. All right? So all we have to figure out is what a is. I'm going to write this. A squared minus b squared. It's going to be equal to a plus b times a minus b. This, even though it don't look like it because it's got an exponent of 4 and an exponent of 6, as long as they're even and you got perfect squares in front, you can still use it. What would a be? This one's let me ask it differently. Because we're trying to write something times something that gives us this. Let me do it the Miss Hall way. To get a right here, just square root that. What's the square root of 9? And what times itself would give you m to the 4th? I know that's weird, but if you square root m to the 4th, you can get m squared. All we're doing is figuring out what a is and what b is so we can plug into the identity. What do you think the square root of 25 n to the 6th is? Square root of 25 is 5. What times itself would give you n to the 6th? N cubed. Guys, I've taught this before without ever bringing up the square root. Miss Hall just brought it up one year and it helped people. I would have asked what times itself would give me 9m to the 4th. It would have to be 3m squared times 3m squared. And then I know I got a plus sign and a minus sign from the little formula. And then I'd ask myself what times itself would give me 25n to the 6th, 5n to the 3rd, 5n to the 3rd. Last one. Look at part B. Isaiah. I got x cubed minus 216. Which one of these identities do you think we might can use if it's got a cubed in it and it's got a subtraction sign in it? Say again. Guys, if you look at this identity, we got x cubed. And I know y'all don't, I'll give you a list of these. I'll give you a list of perfect cubes. Like perfect cubes are 1, 8, 27, 64. 216 is a perfect cube. And if you don't know that, I'll give you a list of them. What you can do here is instead of square rooting, you could take the cube root. All we're trying to do is we're trying to figure out what a is. What do you think happens when you cube root x cubed? Just x. The cube root of 216. Again, I'll give you this list. The cube root of 216 is 6. That means what number times itself 3 times will give you 216? And it's 6. So for that identity, it's just right over there. It says a minus b times a squared plus ab plus b squared. We just found x. A is x and b is 6. So just x minus 6. This says a squared. So x squared. The middle part's a times b. What's 6 times x? Just 6x. And then my last part says b squared. So what's 6 squared? If I plugged in 6 there, that would say 6 squared. What's 6 squared? So this factors to be x minus 6 times x squared plus 6x plus 36.